What's the smartest way to justify your
So for those questions, I think the most important, those won't be so much like justification questions. They'll be more just like, did you get the right order? But they can be like fairly like high level explanations. Like if you just say like any polynomial in n is going to be asymptotically higher than any logarithm raised to the power or something like that, or exponential functions are higher than polynomial or whatever. So as long as you sort of have a gist for, I mean that's the main classes of functions we talked about. There's logs, there's polynomials, and there's exponentials. So, I mean, do you have any questions regarding how do you order within those classes, or I think sort of that's the.
Well, I mean, it just seems like the justification is your answer. If I order one before the other, that's
Yeah.
Yeah, exactly.
Yeah. So I mean that's the like on such a question you wouldn't have like a proof of like why that's correct. And if it was one where it was proved why something's asymptotically higher than the other, they'd be like we'd ask you probably to do 2 instead, and to say prove this formally or whatever that this function's an O of this, and then that there you're like working specifically with the definition of big O or whatever. But for if you have to order several, and there's no way we're going to prove for every pair that that's the reason why it's the case. So. Yep.
Number 4 on that same test.
You give the problem. We don't have memorized.
Okay.
And what about it?
There's the you have n biased coins, and they're looking for exactly k heads.
Okay.
You want to pick the probability in nk time. How do you prove the at one time?
So the first, yeah, if you want to. So does everyone know this? Has seen the practice exam and knows this question? So does it give any details of like how to? Okay. Well,
Sorry.
does it tell you what strategy to use?
And watching one time was all in K.
Okay, but it says use dynamic programming, right? So that's like your first. Okay. So do you did anyone try this one and come up with something they think might work? Yeah.
So I figured you could represent it as a tree, where the first level is the coin 1, and then you basically have a split, like the probability of getting a heads, and then the probability of not getting a heads.
Okay.
And then the second level could be the probability of getting a head for the second coin, and then not so, and so on and so forth.
Okay. So
and when you traverse that tree, the edges end up giving you the total probability.
okay. So in terms of so you're sort of just like expressing the entire probability space, but because there's like not heads for every flip you do, how many different for n flips, how many different possibilities are there in terms of outcomes for this experiment?
And choose k.
Mm-hmm.
Choose to the end.
To the end. So you have think of a binary string of like that. 0 corresponds to heads, 1 corresponds to tails, and how many? You're gonna have 2 to the n number of possibilities there. So in terms of like this would require like exponential amount of space, and since you're trying to figure out exactly k heads, there's going to be several branches of the tree which you have to like figure out. So in terms of like what you're trying to do, usually in dynamic programming algorithms, you have some problem where there's an exponential number of solutions, but you're trying to get rid of that and not do brute force. And so you're like hiding that by sort of doing these like recurrences. We're sort of hiding the need to do that in terms of by grouping eliminating several solutions for every recursive step we define. So I don't know, do you want to go through?
I actually think that this solution won't be exponential, but right there are n choose k different ways of getting k heads. So if you traverse all of those paths down the tree, then that's like n to the k different paths, right?
Right.
Each
So
path has some
it's exponential in size, and then for an n choose, yeah. So n choose k can be as bad as what? What's the worst case for n choose k? N choose n. What's the biggest value of? If I have for k, how do I maximize n choose k? Yeah. In that case, you're going to be close to 2 to the n. You're going to have 2 to the n minus 1. Things that you're close to that. So yeah, this same thing. Go over.
like in general, to solve something with dynamic programming, you want to write down a table and then fill in the table in some way such that each entry in the table is calculated with entries that you've already filled in the table. So to figure out how to calculate a new entry in the table from an old entry in the table, you need to write down some sort of recursive like formula. So the problem we're trying to solve is the probability of getting k heads in n flips. Is that right? So what are some good subproblems?
One heads.
Okay, so one heads and one flips.
Well, yeah, then at the end.
And then, yeah, okay, so in general, if I'm trying to figure out k heads and n flips, good subproblems are a smaller number of heads in a smaller number of flips, right? So I actually want to do this for all things smaller than k and for all things smaller than n. I want to get all of those subproblems. Does that sound like a good strategy? And the runtime gives you a hint because the runtime is n times k, which would be the size of a table that has n times k things, which is just all of these entries. Okay, so let's try to do the. So the table will fill in.
Minimum work.
So this will be h heads in n flips, okay? That's what this table is. So if I pick any h along here and any m along here, then this entry in the table should be the probability of getting h heads in m flips, right? And then the maximum entry here is k, and the maximum here is n. So at the very top right corner of the table, I get the probability of getting k heads in n flips, which is what I'm looking for. And so I want to figure out some way of filling in this table so that I eventually get this top right. So I can fill in some of the table, right? I can fill in the ones down here pretty easily. The probability of getting one head in one flip is what? Piece.
This is constant for every flip, right? This is p.
No, it's different probability.
It's different probability for every flip, so p.
So one head in one flip would be p sub 1, right? And 0 heads in one flip would be what?
1 minus p sub
1 minus p sub 1. Right. So this is sort of our base case. We fill in these two entries. So now, in general, I look at some entry, p sub hm, and I want to write down this probability in terms of other p of something something, where the something something are smaller than h, or smaller than or equal to h, and smaller than or equal to n. So how can I do that? Yeah.
Well, it's like you already have h heads and you want to get another head.
Exactly. That's one of the cases. Good. So you're saying if I already have h heads, I want to get not a head. So that case is when I have h heads already and m minus 1 flips, right? So the probability of this is going to be equal to probability of h heads already in m minus 1 flips times what? 1 minus pi, which is the probability that I get a tails on this flip.
Not pi.
P, what?
What do you want for an index there?
So,
Just looking at the indices up there. So I is sort of this is a generic index, but
M, yeah. So does everyone see that? So this is the probability that in m minus 1 flips I had h heads times the probability that I get a tails on the current flip. And that's part of this. What other way could I get h heads on m flips? There's only one other way.
P h minus 1 m then times p hat.
Pm times what? Sorry?
So it has like p hat and the probability of getting a hat on a single flip then times
Yeah.
then times the ph minus 1 times m minus 1.
So the only two options are that in m minus 1 flips, I either have h heads or I have h minus 1 heads. Or, sorry, those aren't the only two options. Those are the only two ways that I can get to h heads in m flips, right? If I have h heads in m minus 1 flips, then I need a tails in this flip. And if I have h minus 1 heads in m minus 1 flips, then I need a heads in this flip. So now I have some box here, some entry in my table, HM. Which two entries in the table do I need to fill in this entry? Yeah. The one right below.
It should be the one diagonally left.
One right below it, and then this one. Yeah. So this is hm minus 1, and this is h minus 1, m minus 1. So using this formula, those are the only two things that we need to fill in this box. And we already said that we can fill in the first two things at the bottom of the table. Or we could probably fill in the whole bottom row. Yeah.
So how would you write something like that on a test to get full credit?
Right.
Like,
So first you'd write down this, right? I have got some recurrence. This shows what your subproblems are, but this sort of defines a recursive function, a recursive algorithm, and we want a dynamic programming algorithm. So instead you say, I'm going to fill in an n by k table, right? Here's the rule I use to fill in the table. And then each entry in the table can be filled in with just a constant number of other entries. Yeah.
So then is the bottom row basically just base cases?
Yeah.
Okay.
Yeah. Right, I mean, yeah.
Because we can assume the computation of those is just constant time.
Yeah. So you say the bottom row takes constant time for each.
Okay.
And then afterwards, I can fill in the table row by row, since any entry I compute in any given row just depends on values in the row below it.
That makes sense.
So given that, this recurrence takes constant time to compute.
Okay.
And then once you have that, what's the last step to arguing the O of n k? It's straightforward.
So does this mean like in that table, all of the entries where n is less than k, that is 0, or n is less than k?
Yeah, all the entries where h is greater than m are 0. So yeah, so you probably only need to fill in like half of this table, right? I only need to fill in things below this diagonal.
Yeah.
Is that important to mention?
Sorry?
Would that be important to mention?
No,
Yeah.
it doesn't matter.
So you just have as much work as if you, so asymptotically, big O notation. or something.
Yeah, or those probabilities are just all 0.
Yeah. So. But back to the running time question. So the last step is I have this table. Each entry takes constant time to compute, given I'm computing it in the correct order. So what's our goal for the running time? Sorry? N times k. So why is the running time n times k? Right. So just mention, those are the two parts. How long does each step of the recurrence take?
So how long does each entry take?
So it's usually, what we've seen mostly is constant time. But it's possible for, like you might take O of n time for each thing. In that case, you want to mention that. And then so how much does each entry take to compute, and then how many entries overall, and then you just multiply the two. So really, if once you have the table and the recurrence, the running time should be straightforward. The trick is coming up with this. So any more questions about that? Yeah.
I have a general question about dynamic programming.
Yeah.
All the examples and lectures were like, they only involve entries like one way or something. Did you ever have to deal with something that was like n minus 2, n minus 2 or something like that?
I mean, it depends on the example. Yeah, I mean, there's like hundreds and hundreds of applications of dynamic programming and like different clever ways and stuff. And there's
So for example, like the Fibonacci numbers, if you're trying to give the kth Fibonacci number, I can do that recursively, but it would take a really long time. And so a dynamic programming algorithm is just fill in the first Fibonacci number, then fill in the second one, and the third one, and the fourth one. And then you need to look to previous. So that's an example.
I mean, yeah, so you can come with examples where it's like where you have to look up for your next subproblem might depend on some like outside array that you have to like look up. So like this isn't -1, but like some value that you have sort of
So this assumes constant.
assume what's constant time?
That calculating the entry.
Well, it depends on. I mean, this is what you have to like solve in the problem is whether like how much. It is possible to come with problems where the recurrence takes like O of n time. Like today, what happened? You went in the class? Come on, man. Awkward. No, so like today we saw an example where you had to, for every time you had to compute something, you had to check n different options of what to pass in as a parameter basically into my recurrence. In that case, we had n squared total entries to fill out in the table, and each one took n time, so that was an n cube algorithm. So that was an example of something like that. So you just have to look at the problem and do the analysis correctly. I mean, it's hard to. There's no rule of thumb that we can really give you in terms of.
All right, more questions?
Would you mind going over question 1 and exam 1?
Yeah, if you say what the
That's
question
the
is.
trivial summation.
Yeah.
You want to do this one?
Do I want to do this?
Trade-off. Or you guys can
Thank
ask
you
the
for-
question.
so wait, what is this guy again?
I equals 0,
J equals 0.
No,
Well, I minus 1.
This is J minus 1.
Yeah, I know.
Okay, so the trick here, it says to give a theta bound, so we'll just do the O. So in terms of, we're just going to do an upper bound here. These questions it's a little bit tricky as to determine, like, you can come up with some, I could say, well, this is like 2 to the n or something, I'm probably in good shape. So like coming up, like doing, like simplifying the expression so it's easy to see the upper bound, but making it so you do it in the right way can be a little tricky, but so we'll just give you some tricks to sort of to get an idea of how you like simplify this. We didn't really do a good lower bound, but well, let's just do the upper bound and then.
Got a pictorial lower bound.
Yeah, pictorial. Yeah. Okay. All right. So who has some ideas on this? Like, what's? If you had a guess, let's start with that. If you're like 30 seconds left in the test. Like there's some clearly right. Yeah, go ahead.
N cubed.
Okay, so n cubed. That's one guess. So what's your get y n cubed?
3 loops.
There's 3 loops. Not a bad start. Although, so what if I just stuck like a 1 here? Would you still guess n cubed?
Yes.
Right. So if I just took this stuff out and I just put a 1 there, what would your guess be still? It'd still be n cubed. So that's a little bit fishy, right? That, well, I'm adding up like i's and j's and k's here, and that if I add this in, it's still asymptotically the same as if I just had a 1 there. So, does anyone want to wager for a higher exponent?
Well, if we replace the I and the j and the k by n's, because the maximum of each of those is going to be n,
Okay.
then we get 4.
So why is that the case?
Because we have 3 loops, but we're summing up n each time.
And so the first loop, what would that be if I sum up? So you're saying like just assume these are all going through n, and then I'm summing up n each time. So what's the first loop?
N squared,
Okay.
n cubed, and 4.
Okay. So these are probably your 2 guesses. So that's like a pretty lax upper bound in terms of. So maybe the lower bound is the trickier part. Eliminating n cubed.
Yeah.
So the answer is n to the 4th.
When we gave this, we just looked for an upper bound.
So yeah, what you said actually, what he said in terms of just sort of make these as like observations that each one of these can be at most n. I can maybe stick a 3 there if you want to be, since there's 3 terms, that each can be at most n. And then these can at most sum through n as well. And if that's the case, then this thing is all n to the 4th. So there is some like room between, and if this is 1, you have n cubed, so there's room in between here. But if you did some analysis like this, like this upper bound thing, so these observations, and you came up with n to the 4th, you get full credit. So this question's a bit goofy. You take that or leave it for what you want. Yeah.
Why is the I plus j plus k not an O1 operation? If it's
Okay.
summing 3 numbers.
No. Okay, this is a good point too, because this came up. So do you want to? This is not this. We're just computing. This is some function of n, correct?
Yeah.
We're just trying to put what class of functions. What's the big O of f of n? Not the amount of time it takes to compute this number. So there's a distinction. So you can. This takes n cubed time because when you're in here computing these are all constant operations, like you said. It doesn't matter if you're summing 1 or summing any number parameter you specify. But we're not asking for how long it takes to compute this thing. We're asking what does this asymptotically, what does this evaluate to as a function then? Just this function. Does the difference make sense?
I still don't see why the I plus j plus.
Because big O's just don't apply to running times. We're just asking, this is just some function.
Yeah.
Big O's apply, you apply big O notation to functions.
Oh, so we're talking about the maximum value.
The value of it, right.
Okay.
So that's an important distinction to make.
It's
There's
a
nothing in that problem that has to do with, like, if you had a computer program that computed this, how long would it take?
Okay.
It just asks, it's strictly a mathematical question. How long does it, what is the asymptotically, what class of functions is
So
this?
I plus j plus k at most adds up to be 3n. And so that's why we get like
Yeah,
3n
so that's the analysis there. But the distinction, does everyone understand that distinction between this classifying a function in an asymptotic class in terms of its big O versus seeing a function and determining what would be the big O running time to compute this thing?
Can you explain it? Just to...
Okay. So in this question, there's nothing to do with, it's not asking you, if you were to write a computer program that computed this thing, how long would it take? So like, when we do big O's, they can apply to anything. Like in your homework, you're going to see it's going to ask you for the asymptotic amount of memory that your program takes. Or usually we work with time. But it doesn't, when you're asking a strictly mathematical question like this, It has nothing to do. We've defined some function in math land. It's not real life. It has nothing to do with computers. This is just like in math land. What's the asymptotic bound on this guy? If this evaluates to some like nasty function that's probably like it has n cubes in it and squares or whatever. But if you were to simplify that thing, what would be the big data? Is what the question is asking. Yeah.
For the steps in this problem, it said for the simplest possible function g. So did we state that the simplest possible function g is then 3n?
No. It's end of the form.
So
It's just saying like this thing when you evaluate this has some closed form. It's gonna have like some n to the fourth term plus some like lower order terms as well. It's gonna be nasty, divided by some constant. Because I mean that's what you do like at this guy. Just go back to like if you sum this up, this is equal to n times what's n plus 1 over 2. So there's an n squared term, there's an n term, there's this constant, but we're just saying just get rid of all that. What the simplest form is this n squared. That's what it's asking for. So it's apply that same sort of simplification to this guy as well.
Give it in the simplest form isn't like very precise language.
Yeah.
And this is from a previous class, so the way the question's asked doesn't reflect the way Damali will ask questions.
Yeah, no, there's no Damali won't ask the questions.
It will be more precise.
So there's
So like, how would something like this be phrased then?
how would something like this be phrased? I mean, like simplest form, he'd probably indicate that this will be a polynomial. So give your big O in terms of just the highest order polynomial or something like that, and eliminate constants. Like that'd be a more concise way to describe that. Yep. Okay.
So the lower bound is also n to the fourth, but it's difficult to prove, and I don't think it's instructive to go through it probably.
Yeah,
So just
we're gonna leave that.
Just don't worry about it.
Does it also
Like-
only ask for one function g of n?
What?
Because it only asks for the one function g of n.
Yeah, so n to the fourth is both an upper bound and a lower bound. So as a TA for this class as well, the theta is there not because he expected anyone to prove a lower bound, but just because he didn't want people putting like n to the hundredth because that is an upper bound. He
That's
wants
fine.
to give a tight upper bound.
Because-
Just show why it's an upper bound, but proving that it's a lower bound is kind of hard.
Yeah, like we couldn't. I don't think it took us some time to think about the right way to phrase a lower bound for this. Like we're not gonna expect you to do that. So. What we want to do, like that analysis that. I'm sorry, what's your name again?
John?
John. What John came up. That's like the kind of thing if you saw a question like this, you'd want to do. Just be able to like kind of parse this thing, and say do something out like this can be at most this, and then we get this n to the fourth upper bound. I mean, and especially if you put like this was 1, that'd be at most n cubed. So this is probably tight, but we wouldn't ask you to because coming up with like a nice formal lower bound for this would be like it takes a little bit of time to think about. So. Anyone feeling better about the test yet? Think they're gonna ace it?
The algorithm, like because this exam is from a different class, the algorithm questions on this exam are probably more like close to what will be on this upcoming exam.
Yeah, like we didn't really on the homeworks. We didn't really ask you to. Anyway, what was the next? You had someone else had a question in the back.
Yeah, I want to ask, so is this n polynomial because you just multiplying it into n that
Yes, yeah. So you just like if we replace this by all these terms can be at most n, and then all these summation bounds can be at most n. So if that was the case, you see why it'd be n to the. Yeah, that's the analysis we did. Yeah.
If I were ready to go for proving correctness, if they ask us for it.
Yeah, so you should prove correctness.
For everything, because I asked that question on Piazza as well, and then the first response said that we needed to prove correctness, and then the professor came in afterwards and said that we didn't unless it was explicitly asked.
Exactly. So every question where
Okay.
yeah.
You
So
do explicitly.
yeah. So I think the instructions on the exam say you don't have to prove correctness unless you're asked to. If a question is asking you to prove correctness, So there's like two things. It's probably going to be asking you to like something specific about the correctness, which is the problem will state. Yeah, I mean, again, and then how far do you have to go? I mean, you're on a test, like what's the sort of like the rule of thumb? Yeah, I mean, this is a hard question. There's like an art to like, I mean, this comes up in your homework, like how much do I have to say? And the rule is you have to convince us, which is, well, how do I do that? It's hard to give a rule of thumb. It's just like, if there's some, the thing to do is like, if you read every sentence, you have, and then you have like you have like since la 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 la, therefore la 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 la. If you can look at that, if you look at that sentence and you're like, why is that the case? Then you're probably missing something in between. That's sort of the rule of thumb. If you sort of look at it and like, well, I couldn't tell you very quickly why that. The only time you're like, you should leave that out is when like the explanation is like fairly straightforward.
Very straightforward.
Like exactly, it's all. I mean, you just have to sort of get a feel for it.
One of the practice tests required the the formula for the geometric sum. Would
Yeah.
we get that, or would we should we just know?
Yeah, I think any formula.
I don't know well.
Yeah, so like all those like closed forms. So you're saying like sum of through infinity is 1 over 1 minus r, and then the other one is 1 minus r to the n plus 1 over 1 minus r.
No.
Yeah.
Either one works. So that's the through n, right? Anyway, those would be, if you're expected to use those in the test, those would be given to you.
Is that true?
Yeah.
Okay. I just haven't seen the most recent copy
Yeah.
of the test.
I've seen more classified.
Yeah.
We go for number one if
Number 1 on what?
I
Sorry, people were talking.
Huh?
On exam 2.
Yeah.
So what's that one? I did a very thorough.
Yeah. Alright, what is it?
It's like solve the approximation. T of n is equal to T of n over 2 plus T of n over 4 plus T of n over 8 plus. And then in this case, it's T of 1
Sorry, T of what?
is 1.
So maybe first off, before we get through it, so what does that recurrence remind you of in terms of recurrences we've seen? Like binary tree. Was there? So you have like these like t of n over like 2 plus t of n over 4, like these sort of like these like multiplying n by some fraction less than 1 integer. So like what algorithm in the running time? Yeah, close to that, but like more explicitly, like that came up. What's that? So yeah, quicksort. You have t of n over 2. Yeah, so one thing I notice about these fractions is what they add up to. If I take t of n over 2 plus t of n over 4 plus t n over 8, it adds up to, which is some fraction less than times n that's less than 1. So does anyone remember like where that was important? What algorithm?
Pertinent search, right?
What was it?
It's in the pertinent search one.
Pertinent search. So the selection algorithm.
Yeah.
Yeah. So do you remember this like selection? The whole point when we like went through and we had like I forget the exact. It's like t of
9 over 10.
yeah. So you end up getting like some. Yeah, I forget exactly what the difference was, but that was this recurrence has a similar flavor to that. So maybe keep that in mind as like you go through. So good.
Yeah, so something like this, I think the best thing to do is like write down a tree and then just add up how much work you're doing at each level of the tree and then say how deep the tree is, and that's it. Alright, so yeah, so I mean if this was just combined into t of 7/8, it would be slightly easier, but it's not, right? like the t of n over 2 will then spawn another t of n over 4 and t of n over 8 and so on. So let's just try to write down the tree. So we have t of n in the top level, and this does O of n. This t of n has the O of n here. And in the next level, I have a t of n over 2 and a t of 4 and a t of n over. Okay, so how much work do I do in this level? 7/8 n, right? Why is that? T of n over 2 does O of n over 2 work. This does O of n over 4 work. This does O of n over 8 work. So,
Be careful with those.
what?
It's, well, at least in terms of like expressing it, it's 7/8.
7/8 times.
Yeah.
Okay. Now, in the next level, how much work am I going to do?
7/8 squared.
Sorry?
7/8 squared.
Why is that?
Because each one of those is going to spawn the same things with the same tree. So the first one you get n over 2 times 7/8, and then n over 4 times 7/8, and n over 8 times 7/8.
Exactly.
You add all those together.
Exactly. So all the children of t of n did 7/8 times O of n work. So all the children of t of n over 2 are going to do 7/8 times O of n over 2 work, right? So the children here, so I have all of the children of any t of n do 7/8 times O of n work. So the children of n over 2 all together are going to do 7/8 times O of n over 2 work. All the children here are going to do 7/8 times t of n over 4 work. O of n over 4 work. And the same thing for n over 8, right? And if I add all of these up, I get 7/8 times O of n over 2 plus O of n over 4 plus O of n over, or n over, yeah. So this is 7/8 times 7/8 times O of n. Okay. So at the first level, I did 7/8 times O of n. At the second level, I get 7/8 squared times O of n. So in general, at the kth level, I get 7/8 to the k times O of n. So now, what's my total run time? Sorry?
Sorry, but this tree is not balanced in the sense which most trees super long at the night.
Exactly, it's not balanced. But so that means at the really low levels, at a low level down here, if I added up everything in this level, I would get, so if it was balanced and I added up the entire last level, I would get like 7/8 to the k times O of n. But I don't have all the things over here, I just have some things over here. So it's definitely going to be bounded by 7/8 to the k times O of n, right?
Yeah, but that would be big goal. Is it like data? Does it equal to data at all?
I mean, you're fine. I mean, you're worried that like the eighth one, when you're dividing by like 8, you're gonna get there much more quickly. I mean, they're within like a constant factor. The heights are, because you're logging by a difference of like 8 versus 2. So whatever like log base.
Yeah, I mean it doesn't matter if the level has fewer things in it, because I'm saying the total work done by the level is upper bounded by 7/8 to the k times O of n. So if I do less work in the level, that just helps me.
Right. So if you trust this up, like if you trust the fact we're upper bounding by it, yeah, let's assume all that stuff's there. Like, and we still get the bound we're looking for, then we're not gonna. He's worried that doing that is gonna be like too much extra work by like ignoring that fact, because the heights might be very different. But
oh, okay. So
but they're within a constant. The heights are within a constant factor.
So you're saying we won't get a tight upper bound, is what you're
Yeah.
saying? Well, okay. So we can see why it's a tight upper bound. So let's just for now trust me that right, this is an upper bound on each level, correct? Even if I only have a few things in the last level, it's still upper bounded by 7/8 to the k times O of n. And it's definitely lower bounded by 7/8 by O of n because in the first, or sorry, I haven't gotten to the upper bound yet, but yeah?
So for these questions, is theta and O notation like interchangeable? I think that's like what.
So no, it's not really. So let's do the upper bound first, and then we'll get to the lower bound. All right. So what's the total upper bound here? If I add it across over all of the levels, it's O of n. So why is it O of n? Well, even if there were infinitely many levels, I don't care how many levels there were. The sum over all of the levels is going to be O of n times 7/8 plus 7/8 squared plus 7/8 to the third, etc. Even if I repeat this sum to infinity, this sum is still bounded by a constant. That's the geometric series he was talking about. So anything less than 1 here, if I do r plus r squared plus r cubed to infinity, if r is less than 1, then this is a constant. Okay? So it doesn't matter how many levels I have. It doesn't matter how long this goes on for, even if it goes on to infinity. This is some constant, and so my total upper bound is just O of n. So why is that why is O of n also the lower bound? Well, in the very first level, I had to do O of n work, so there's no way I can get faster than that. So that answers your question. Yeah.
So what happens when the lower bound and the upper bound are not going to be like it's like the same, I guess like factor or like how do you write the theta notation for that?
So I'm not sure what you mean. So you can write an.
So if you found that the lower bound, right, for some other example problem was going to be like O of 1, how would you write the final like theta notation, given that your big O notation is going to be like O of 1 squared or something else?
I mean, it depends on.
So it's impossible for the highest lower bound and the lowest upper bound not to be the same, right? You can find some lower bound that's lower than some upper bound, but that means there must be a lower upper bound and a higher lower bound, just by definition, right? So, right, because there's no one answer for upper bound and one answer for lower bound. There are many answers.
Is that
But
amount of work sufficient then on the test?
this amount of work?
Yeah.
Yeah, this is completely fine.
So for this kind of question, we don't need to give an induction proof for advice like 7 or 8.
No, you don't need to do it.
Yeah.
You just say the sum. You just show two levels. Say this now. Therefore, the sum in the kth level is 7/8 to the k times O of n. That makes a geometric series, so it's O of n.
Okay.
Yeah.
When do we need to use the inductive proof?
When it asks you to do an inductive proof, probably. So yeah, don't if it does. There's no inductive proof. Like that phrase doesn't pop up in the question. Don't start doing inductive proof.
When you're setting the lower bound, when like the number inside the bracket goes below 1, it doesn't like go to negative numbers.
No number inside the bracket. Which number inside the bracket?
Well, like if you go down infinitely in the trees, and like the numbers inside the bracket like n over like 2 over k, 2 powered by k, that's gonna go below 1, and it's gonna be like 1 over half and 1 over 4.
No, it'll never go. So I mean, these recurrence relations, I never go below 1. Right? I stop when t of 1 is equal to 1.
But like when you're splitting like t of 2, you're gonna have like t of 1 and t of like 1.5 and
1.5.
Do you mean 1/2 and stuff?
Yeah,
Yeah, just do like assume
Yeah,
it's,
so integer division is fine.
so you can do like t of 0 is 1, t of 1 is 1. You can define as many base cases as you want up to some constant. So like if you would try to define O of, let's say, if it makes you happy, you could do everything below 8 is 8 and below is some constant.
so we can like just assume that all these numbers are integers.
Yeah, and everything will be. This is all integer division. N is some number of objects, or some like n is the size of your input in bits. You can't have parts of bits, like things like that.
So the condition can be specified in the problem.
No, that's just sort of
Just
assumed.
don't worry about base cases. Really. We're not going to.
So we don't need to say like n is greater than
N is greater than
8.
no. It's just yeah.
Like asymptotically, it's like there's like.
As soon as n is an integer, t of n is just. As soon as n is a constant, t of n is also a constant. You can pick any constant you want for the base case, and it's just all integer division.
Yeah.
So at the beginning, like you talked about how this problem was like different than if you just had like t of like 7/8, 10. But I was wondering, when I looked at this, I saw that like the t of n over 2 number part was going to dominate over the n over 4 number 8. So that was kind of going to be the bottleneck to determine the runtime. So can you ignore the others and just deal with the runtime of the t of n over 2?
So that
sometimes, yeah.
It,
You're gonna
it
get the same answer.
It kind of works in this case, but it doesn't necessarily work.
Be careful there.
So be careful. So it works in this case because these are each halves of this. But if it was t of
if you had an extra t of n over 8, what happens?
Right. So if this was t of n over 2 plus t of n over 4 plus t of n over 4, then it wouldn't work. I mean, even if this was like t of n over 2 plus t of n over 3 plus t of n over 4, then you can't just ignore the n over 3.
Yeah, it's like getting so you have to be careful if you're going to do that.
Yeah.
I probably wouldn't write something, like I would probably try to expand it out and then reason from there. Just since that's not like that rule of thumb breaks down very quickly if you change constants.
Yeah. It happens to work here, but not in general.
So would you recommend that we also use drawing out the tree and finding an method and then we just
Yes. Yeah. Okay. Which one is it? Yeah. Just can you like describe it? Okay. Yeah.
So it's problem 3 on exam 2. I think it's like you're given an undirected graph and you want to return like a path that traverses every edge exactly once or twice, I think.
Yeah.
Once in each direction. That's right.
I'm going to do it. You want me to do it?
I don't think this is gonna. We're gonna like rate it like a ton. So did someone try to solve this? Someone have an idea? Problem 3 on a practice exam 2. One. Okay, I was wrong. Practice exam 1. Yeah.
So my idea was that.
Okay, hold on. Let's. Okay, hold on. So we have an idea here. So people were good.
My idea was that, well, we know at DFS,
Yeah.
it's every single edge twice in our search if there's no back edges.
Yes, that's true.
Yeah. And so whenever we can run a modified DFS, and just whenever we see a back edge, we traverse that and then come back again. And that allows us to hit every single edge twice.
So that's almost perfect, except so here I have. Okay, so you just traverse back edges and not forward edges. Is that what you meant? So here I've got a back edge, and then maybe some more tree.
Yeah. And so you would just.
So when do you traverse this edge?
When you get down to that child element,
Yep.
right here, you just go up the edge and then back on the edge again.
Okay,
To get back to where you started. Yeah.
So from here, it's a forward edge, and so you skip forward edges and just traverse back edges.
Exactly.
Awesome. So that will guarantee.
And cross edges you treat like back
So
edges too.
yeah, there are no cross edges. So you're fine.
What is this then?
DFS. Said.
Right.
So did everyone understand that? No? Okay. So I have some graph, and I'm going to run a DFS on the graph. Okay? Now, assume that there are no back edges for a second and just look at all of the tree edges. How does my DFS look when so here's my DFS tree, but what is I need a path that traverses every edge twice. So what did my DFS look like? I went all the way down here to this node, right? And then back up here, and then back down to this one, and then back up here, and then back up here, and then back up here, and so on, right? I'm just sort of walking my tree like this. So I hit every tree edge twice, exactly twice. So this is a path that hits every tree edge twice. Okay? The only additional edges in my graph that I need to include in my path are forward/back edges. There are no cross edges in a DFS, so I don't have to worry about those. So I also need to hit all forward and back edges. So
in terms of DFS, like it's undirected graph, that's why. That first search in directed graph is.
yeah.
So it's an undirected graph. There's no like the cross edge can only happen. That relationship only pops up if you have like some other subtree that would have traveled to the other subtree, but you already searched there. But an undirected graph will just take that edge, so you can't have such. Right. Okay, keep on.
So I put in some forward/back edge, and basically I have two options for when to traverse this edge, either from this node or from this node, right? And so his idea was to do it in the reverse direction. So if I get to here, this is a forward edge because it's an edge to a child, so I won't traverse it. But when I get here, the other end of the edge has a pre-value that's earlier than me, so I just traverse it twice.
Does it matter whether you traverse at the beginning or the end?
No.
As long as you're consistent.
Okay.
Right. I can't traverse it from both of these because if I traverse it twice from here and then come down here and traverse it twice, then it's too many.
So you as long as you only do one.
Yeah. Exactly. Yeah.
The differentiating algorithm, how you would tell the difference between the two edges, so just be like, oh, that's what my algorithm would do.
Yeah, so how do you tell the difference between the so in the class on this he gave like an easy way of telling the difference, right? It's just based on pre and post values. If I've never seen a node before, then I explore that node and then it's called a tree edge. And if I have seen the node before and then its pre-value is going to be less.
In the answer, will we need to, I guess, explicitly say that, I guess, when we're proving that, I guess we would prove the correctness of it.
Yeah.
That'd probably be a good detail to mention. Like if you don't mention like how you would maintain this, you should probably just at least have a sentence in terms of like we could store pre-values or we could keep track of something that like some value. It's not like some here like the fact it's pre versus post doesn't matter. There's probably other ways to like mark the fact you like some marking scheme, but like just describe that briefly. Would be a good idea.
I was gonna say then I'll just mark it when you hit the edge of the first or the node the first time, and then if you come upon an edge that needs to that you're already marked, then you can just
That's also
return and come back.
You return and come back, yeah.
If you do it that way, you can do it with any kind of search tree. You can do a BFS search tree and it still works, even though there are cross edges and stuff.
Okay.
Yeah.
Can you just explain correctness proof for running time too, maybe?
For running time,
Or well, just the proof of correctness. How do we do correctness?
so the proof of correctness is kind of trivial in this case from the way I've done the algorithm, but the proof of correctness needs to say that it's a path, and the way that I've defined it, it's clearly a path. I never jump from one node to another node, right? In this exploration, I'm just doing a DFS, and then each time I see a back edge, I explore the back edge in the back direction and then the forward direction, and then continue. So that defines a path. And then why will I get every edge? Because every edge in a DFS tree is either a tree edge or a back/forward edge. And I just explained why, like how to explore tree edges and back or forward edges. So that's all you really need. And then the running time.
It's every edge.
What?
It just sits every edge once and every node once.
Exactly.
You're running a DFS. So
You're just running a DFS. So
you know that simple sense.
Can you go to the next one too?
Yeah.
My confusion here was how was it? whether we can transform this idea into code, or like rewrite that into like standard in a way like everything.
Yeah, so this would be a type of question where it would be pretty hard to write pseudocode, and maybe it wouldn't be that hard, but it would definitely be hard to read pseudocode. I would definitely, like, for this, I would give an algorithm the way I just said in English.
We can actually write pseudocode.
What?
We can write pseudocode.
No, you don't need to write pseudocode. Yeah, don't worry about that. And if you do choose to write pseudocode, please write pseudocode and not C code.
Yeah, don't put like public and that'll hurt my. If I like have to like remember how to code in Java and I read your code, I'm gonna be like, yeah, this is awesome.
How do you feel about
Put it in the Java file and create it later.
So like if we were section 1,
Sorry?
if you were on how do we have
How would you remember your parent?
Whatever you
So
set to package, you're gonna go up.
you can just look at pre and post values. I mean, I guess the way you do this, I guess the way you can do a DFS is with a stacks, right?
You just have some, like you can just do this recursively. You pass in some array that marks, you create like a 0, 1 array that I put a 1 there if I visited, 0 otherwise, or you can put the pre-values. And every time you're going to recurse and do a DFS on some node, you look up in that array to determine if you should do it or not. And then if you want to like output the path itself, every time you call a DFS on the next node you're searching at, you just keep some global string that you keep passing in, and you keep concatenating every edge that I visit, like add on to that string. So like, but these are all details that don't matter, like what we're trying to say.
Yeah.
So like, for some of the algorithms, like for extras and volume 4, like he uses like a min heap for extras, I know, right? So like, the implementation that I was familiar with uses a priority queue, and then that way it would work in both of them. It just like automatically puts in the one with the lowest weight.
And that would what?
It would just automatically like put the one with the lowest weight first.
Yeah, but how are, like, priority queues are implemented with menus, right?
Right, so I guess like if we use, like if you were to say like use a priority queue and test that wrong, or like.
Yeah, like any basic data structure you've seen in previous classes, and you can assume like the guarantees, yeah. For me, a priority queue and a min heap, there's not much. I think there's just some like implementation, or like there's not a big distinction there.
Sure.
But like data structures from previous classes, if you want to like say I could do this, like you can assume those.
I guess because like the min heap doesn't work for negatives, for the priority queue might.
Why wouldn't?
I mean, a priority queue is sort of like an abstract data structure that has some properties, and then there's some way of implementing the priority queue. And one way it's often implemented is using a min heap. But if you wanted negative numbers, maybe you
okay, yeah, no, that's
like
different
things.
Yeah.
But don't worry about it. The only thing you shouldn't do is use data structures that are like specific to some programming language. Like don't say use like a dictionary or something from Python.
Okay, so you said you wanted to go over the next one?
Yeah, it seems like it's relatively similar.
Okay. So this is the next question, the same exam. I think it's detect if there's a cycle in a undirected graph and O of n time, or the size of b. So that's the, yeah. It's alright. So this will be the last one we'll go over, and I'll stick around at least. I don't know if you have something to do with it, and maybe ask like lingering questions. But. Okay, so quickly, who had an idea here? Yep, looks like you. Okay. That seems like a common theme with these questions. Yeah.
It's not like
Yeah. TFS.
Yeah, it's not a hint. This exam was
this is hint for this
DFSs,
exam,
but it won't be that.
Yeah. So yeah, remember to. I mean, these are good practice in terms of like the level of difficulty and the type of like reasoning you want to like try to get out of your questions. But the material. This is another class, so I don't. The material covered in the first half or whatever of the lectures is going to be slightly different. So keep that in mind. So I use these as sort of practice in terms of like puzzles that like what kind of thinking do I have to go through to solve these, but the material might be slightly different.
Yeah, the answer to everything won't be DFS.
Yeah, so if you're although I don't know, an expectation, if you knew nothing about the exam and you had like a bunch of blanks, you just wrote DFS for the rest of them, I think an expectation that might be like one of the better strategies. Just saying, that's maybe not for this class, but over if you averaged over all exams given by all computer science professors everywhere in the United States, DFS. Anyway, so idea. So yeah, DFS. What about DFS? Why is it cool?
Because the max number of vertices or edges you can check is n-1.
Okay, so
What minus 1?
n minus.
N.
So like what? So in terms of, can you reason through that a little bit more? So like, what do you mean by the max number you'd have to check?
You have like n vertices, and you go through all of them, right? And then once you get to an edge that split the vertex that you want to move into, then you know that there's a cycle.
Okay, good.
So the max number is like if you do this, and that's n minus 1.
Right.
And for a long edge,
So yeah, I think that's roughly the right idea. So like I think the idea is that any graph on n vertices that has n edges, I'm guaranteed to have a cycle. Because a tree has n minus 1, and at that point I'm acyclic. If it's connected, we're assuming it's connected, and it's just better for me if it's not connected, because then I have like smaller subgraphs that are more likely to have a cycle. But once I have n edges, I'm guaranteed to have a cycle somewhere. So if I just run my DFS, and what was the step that you said, as soon as you observe like a back edge, as soon as there's an edge that is not part of my DFS tree, that I'm looking back at some vertice I visit, that guarantees I have a cycle, right? Because I've taken some path from wherever the back edge is to, I've gone to some other vertices through a path, and now that back edge completes the cycle. So the point is that as soon as I have more than n vertices in my graph, I'm guaranteed to observe a back edge.
Edges.
I'm sorry, yeah.
So do we even have to do the DFS, or can we just count edges? If E is greater than, once E is greater than.
So if it like, well, how does the question phrase?
Yeah, you can't just count edges because the graph might not be connected.
But
I can have a graph with a cycle that has well less than n edges if I just have lots of vertices sitting by themselves. So you do have to run the DFS. But that's a good point. If the graph was connected, you could just count edges.
So what's the?
If the graph is connected, you can count edges at n edge.
So okay, I think the question should be phrased: if it has a cycle, output the cycle itself. Then you have to do work. If it does the question just say, does it have a cycle?
Yeah.
Okay, then you could count it.
No, you can't, because if the graph is disconnected, if the graph is disconnected,
so that's what happens.
It has a bunch of vertices.
I can have a cycle of 3 and then a bunch of vertices, and then it has like way less than n edges.
Yeah. But then m is less than n.
Right.
So you're comparing m to the number.
So you're saying output a cycle if m is less than n. I'm sorry.
M is greater than.
Yeah, it wouldn't work if it's not.
It wouldn't work if it's not connected.
So wait, what's the, but no, I'm confused.
And the counterexample.
There's a bunch of vertices with no edges on them, and then one small component that has a cycle.
Oh, I see. Yeah, no, you're right. Yeah.
A lot of people tried doing said that last semester.
Yeah, no, that's right.
Answer to this problem.
So yeah, if it's you need to do the DFS just to see if there's the kind of.
So we just do DFS.
Yeah. See, I mean, if it's
what we've already been to society.
yeah, if it's disconnected, you have to do like multiple DFSs. Right? Yeah.
So like, if you don't detect one, do it in your DFS finishes, but yet there's still nodes that you haven't marked.
Yeah. Yeah. A lot of people just, when they say do a DFS, they mean if the graph is unconnected, just keep doing DFS.
Alright, is that it?
That's usually it's cool. You'll just see this is Josh. I've seen like 60 people try to answer this question. Yeah.
Oh yeah.
So you're so I don't I can vary it I don't really try to tax practice Would you? Are you able to? I mean, all the tax practice out of speaking English. Like, you know, he gives you reps, like for each letter, he's got reps. That's two of them. Yes. Because you have. I mean, what is it saying? Yeah. For us, everyone that's it's stated. You are. This is Chinese. So this is true. But the entire time so the way I respond to my mom is to know how to do things, but you don't need to. It doesn't matter. You can have this like the same definition. You don't have there's some constant I can take. You won't be asked to like either explain this or you can pick on. They have the same.
So he wouldn't be like use.
If we switch to like use it's a use what? No. The point is that he doesn't want you to memorize units. He wants you to figure out new things that you haven't seen before. Which you subtract both makes it harder and easier. Less memorization, harder tests. Just like once you get to the so this
In the one homework test question, we had like a whole bunch of functions that we were trying to list them in order of like how they're asked about the sound. I was going to ask you like if you have like a function,
so the path is just like contained
and you want to determine
you specify
how to compare it.
Right. I'm just doing a traversal of the DFS tree, but each time I see a back edge, I'm going back and then forward up.
A comparison with that. That's all the cases to see like how it's grow for each edge. Making a comparison. That's benefit functions. How would you do it? Just
so like what were the like one you had like
one of them was like
the first one's log of something. So if I have like that 100, so any increase but your estimate change.
Log squared. Log squared of n means
so the next one's like log
squared. And then the log of n to the squared power means log.
So like log squared, log third.
So it's literally just comparisons.
And
like
this power is equal to 100 times log n. So this is actually
the next one after that. It's like the next big and there's like 0.0.
n factorial is kind of like n to the n. So it's going to be bigger than 1. That's something to the n.
I assume there's a lot of
So it'll be bigger than
slower.
That's all the way to
because,
the
I mean,
end.
like,
then
So like, why is that? Why is that?
Yeah.
So bases are
almost the same, but 2 to the 2n,
So why is 2 to the 2
is equal to 4 to the n, so it'll be bigger.
Because it's gonna grow faster with two
Oh, sorry.
exponents.
Good. In terms of, you can assume that any base, if I have a to the n versus b to the n, if
Actually, I thought that's
b is
same.
bigger
That's
than
same
a,
topic.
Then it's going to grow faster.
then b is going to go.
Okay, how do you tell whether this log
And then how would you formalize that difference?
log of n? Yeah.
I mean, what's the algebra there?
What? Like, how do you compare log and
Like, what is this equal to?
So,
log? So
2 to the 2.
So log of n squared is a polynomial in log n. Right?
Okay,
So
and
that's
you can
what it is.
compare them.
Square root of n is n to the 1/2, which is a polynomial in n.
So
So
what
it
is
doesn't
this?
matter what a polynomial is. I mean, as long as it's a constant. A polynomial in n is always bigger than a polynomial in log n.
And 2
Alright, yeah, sure. So it doesn't matter if this is 100 or whatever.
N to the n minus 1. Because this is n
N
minus
minus
1
one.
times n minus 2, and this to be bigger than this, but n to the n minus 1 is
Like, how would you, like, create?
like that. This is the biggest one. I want to argue for why this is bigger than
Square
40.
root of n. So if you have like t of n.
So that's never gonna. So I want something that's
T,
like
like square root of n plus whatever, I guess like that. Like, would you be able to use
so
it?
take something that's called like the midway point.
And
Kind of like that. So
Like, what do you use?
It's n over 2 and n
So
over
if
2.
you.
So I used a tree because the t of n had multiple
So you think
t's
of
like
like
this.
that.
Right, so each one, if I only have one t on this side, the tree is just gonna be like a sequence of phrases
Yeah.
going down.
But let's say that you just have
Right.
like
So
two.
in the factorial, there's more terms. This is just some subset of
Like,
it.
is there some way to solve?
But then I have something like this. So I have like n to the n here, essentially.
Like, how
So
would
you
you
have n
solve
to the. So what is this? This is 1
Yeah,
half.
so because of the two here, I can say t of n, and then each one of these is going to be t of root n,
Times n, yeah.
t of root
Okay,
n,
and
So
then
this is
and
just.
so on.
with any significantly larger,
So-
this is going to be.
What? How does this compute? Okay, so each
Like,
level
once you have
will
n
be
over
t
2,
to
that's gonna be
the
bigger than.
1 over
I mean, this.
2 to the k.
Well, it's going to be larger
k
as soon as you
level,
have,
and
as soon as you have
there
an
will
n
be,
here and an n up here, no matter what the functions of
2 to
them
the
are.
k of them. at the k
Yeah,
level.
just to make sure. So like
So
you.
first, you need how much work is done in each level, right? Which is just 2 to the k times n. So you can figure out how much work is done in each level, and then you need to figure out how big the tree is, the depth of the tree, right? So what's the depth of the tree? It's the point at which
Yeah, I mean, as soon as like,
n
n is bigger than
1 over
like
2 to the
4,
k
it's
is equal to
so like assume n is 8.
say 2, I think.
Did you
it's
assume
So
that
then,
n
yeah,
some
n is
constant.
bigger than 8.
Right, so this will give me how deep
Okay,
Okay,
let's do 10.
so how do I solve
As
this?
soon as n is bigger than 10,
Take
it's
logs
bigger
of
than
both
n
sides.
over 2.
And now I
5
add
then over 2,
1 over
which
2 to
is-
the k.
You can,
is equal to
you can take
log
out
base
the,
2 of 2, which is just 1. Right?
you can add on the n to the 1. Okay, that's sorry.
1 over 2 to the k times
And one
log
last
of
question,
n
how
equal
should
to
I
log base 2 of
prioritize
2.
my time studying? Should I look at the homework questions, look at the notes,
And then I
which one
multiply
do
by
you
2
think
to
more
the
helpful?
k.
Yeah,
Log of n is equal to 2 to the k. And now I take the logs again.
so the homework questions only covered up to like, what was the last homework question you guys had? You had like some,
right
you had a lot of like
before-
divided.
didn't have any graphs. It was right before we started.
Yeah, so,
log n. So there's
So listen,
log
we
n.
have homework for the homework two.
Yeah, that's
Yeah,
what I was
like almost
saying.
like,
Is homework 2, like the stuff on that covered on the exam? Like,
yeah,
should
so
I,
yeah,
should
it's
I
up to
look
network
at those
flows.
as kind of
Yeah, so like I honestly I'd probably like look more at like the stuff, the material in class. Like there's
The lectures?
yeah, the lectures like sense like
So it's
include
this
so like the homework
times,
stuff. Like make sure you know that. But my guess is since you did a homework on that, you'll probably know it a little
This
bit
is
better.
the
So like the latter stuff you haven't been examined on essentially.
like graphs and network.
Yeah, graphs and I would
yeah.
like definitely make sure you understand. I mean, he told you today study dynamic programming, so that's a pretty big hint. But like all the other lectures, I'd go make sure you like understand those. Like if he ever gave you like, hey, like this is an exercise to do on your own, like so that's another like good thing to do. And like don't memorize proofs. We're not gonna ask you to like reproduce a proof,
Yeah.
but like if you
If you can understand how the algorithm works, it's good probably.
yeah, so like the knowing the proofs will like, or at least if you're able to walk through and understand the proofs, you're gonna extract like a lot of properties from that, like that might be useful. Just to like knowing like facts about network flows, or like knowing like what exactly was that like min cut equals max flow theorem, like stating like that's
Like nothing in class today is going to be on the test, right? Nothing
the dynamic programming is like dynamic programming is on the test, but he said like the data structure stuff.
New he introduced today.
Yeah, nothing. But nothing new.
Yeah, nothing. I mean, you can call that binary search stuff. It's another example, but yeah.
And so I just set that as some constants. I chose 2 because I'm going to use base 2 logs, so it'll work out better. And now I just want to solve this equation for k.
That's for this class.
Okay, that makes sense.
And so
Oh,
I
yeah, that's
log
not
n
bad.
and debuild it. We're going to take the log of each side.
Maybe the
here,
second half you'll have a lot
and
more
I
hits.
get log n times 1 over 2 to the k is equal to log base 2 of 2, which is just 1. Okay, so I've got log n is equal.
Multiply 2 to the k over, yeah.
And then I've got log n is equal to 2 to the k, and then I take another log, and then I've got log.
Okay, so then if it's a square root, generally it'll be log n. And if it's a log that's getting cut in half, then it'll just be log n.
And also out of curiosity, compared to like
And then you'll multiply that though by
the
whatever
homework, sorry, the practice tests we have from like previous
So it
years.
depends, like a
Is this
little,
professor
I mean,
harder or
it depends on if there's a 2 here.
I'm gonna guess hard.
Wouldn't there be like?
Yeah, I mean,
so it's like 2t.
He's like lowered the
So what
difficulties
is
of the
that?
class is going on as well, because I think he's like realized.
Right, so I still want to see how long this goes, so this still works, so I have k levels.
So it adjusted.
And
And
in
this is
each
first
level
thing
I'm
he's
doing,
doing. He's like trying to feel out like what was the right like
and so
pace to then teach the class at.
1 over 2 to the k work, right?
Yeah, I don't know. I think you'll get like there's a sweet spot. Like I don't think just making it easier is always the right call in terms of like because sometimes you don't get as much out of it. Even like if you make it so like more students can like do it like easily. So I think this class, like in my opinion, should be it's like a little definitely somewhat of a
that, right? Like
camp class where
T
you
of this.
like you pushed a little bit,
Is
especially
equal
since you
plus
guys. It doesn't
K
seem like there's a lot of like math classes that you have to take, and this is like the one math class.
At the
that
K
you have
level.
to.
I'm EC COMPSCI, so.
Okay.
There's
So
loads
if there's
of
a
that.
2 here?
Yeah. Okay. Right. So. But I mean, just as a like, I think there's you can definitely go through the
anytime
major
I
here and not have to
be
take like
this,
math except for this class. So.
times k.
You have to take discrete math and this, and that's.
Right, and sometimes yeah. I mean, I just
So the
don't
word
think one
detail-
math class before.
Oh, sorry. The word detail will not.
So I think that's.
Yeah. So it's
Given that, like, I think this should be like for anyone, this should be a tough in the sense that it should definitely prepare you enough to like have like some level of mathematical maturity. I don't know. That's so.
As ECs we come up with these.
Yeah, it's a different kind of. It's a
Yeah,
like
which
see
is
like I'm
very-
not like see I don't like work with a lot of like new stuff. So it's like with this like discrete math, it'd be nice if you guys had a little bit more of it.
Oh, and
Like seeing induction curves and some of these like.
a real math course anymore.
But
Yeah, I think we're
so what we
discussing
did was,
that. So I think discrete math had definitely. I think it's
we
an
did
interesting class.
that
Some
until
people.
we
It
found
sounds like a
this.
very interesting class, and you learn some.
And then we
very
stopped.
things.
Yeah,
But
So
it's
if
not
we
like
kept on
really
going,
like
it would have been O of n.
It's like
Yeah,
functional
but
learning.
because we
Yeah.
stopped
So
and find
it's not quite
we're
like
guaranteed for only to be
Yeah.
I don't think anything in that class would really help you out here. I think they were talking about
O of n.
making
Because
sentences that way.
If I haven't found a cycle yet,
Correct instead of prereq.
then I must still have a tree.
But that should be. It really should be.
But
like
I
something
found
that's
that
like
all the
me,
edges
like,
I've seen
and
form a
choose
tree.
is,
And in a
like,
tree,
Yeah,
there are only
like,
n
choose
minus
that
1
in that case.
where n is the number
That
of
should,
instances.
like that should those like facts should be weeded out. In that
Right.
class, but-
So I've only like I'm done O of n.
Yeah, I mean, like we're doing like crack RSA, like you know.
Like the trick to that problem was that
It sounds like yeah,
coding
yeah.
problems.
because
That's
I was
like
stopped
something
on
about
the cycle,
yeah,
I didn't
like,
have to go
something
and look at
something
all
like
the these
that,
extra
right?
edges that would have added
topics
O of n.
that I never like covered stuff like that.
Yeah. So their answer
Yeah.
was to like add another problem set. So
Yeah.
they're adding a probability problem set. So.
Okay. Yeah, it needs probably more change than that.
Yeah,
Yeah.
It needs so much work. It needs to be a math class. I don't know what
Yeah.